Okay, thanks for the introduction. I'm Yilu from Penn State University. Today, I want to present our work. Today I want to present our work, a systematic threat analysis and practical attacks on automated frequency coordination systems. This is a joint work between Penn State and Idaho National Lab. First, to understand the problem, we need to understand why is AFC critical for 6 GHz. We know that traditional 2.4 and 5 GHz Wi-Fi systems are already congested. In that case, the Wi-Fi Alliance newly introduced the 6 GHz frequency for higher bandwidth and faster speed. However, in the United States and some other countries, the new 6 GHz spectrum is already used by mission-critical incumbent systems. They are used in emergency communications, cellular backhaul, and other kind of wireless connections. So the automated frequency coordination system, or AFC system, are introduced to manage the spectrum access and prevent the interference between the newly introduced Wi-Fi APs and the incumbent devices. Talking about the incumbents, we are mainly talking about fixed service links in the United States. They are point-to-point wireless links also operates in the same 6 GHz frequencies. And the AFC system is designed to protect this kind of licensed wireless equipment. Let's talk about AFC system a little bit more. So as we discussed, the AFC system coordinates the spectrum for Wi-Fi APs to avoid interference with the incumbents. The whole workflow is that first, the standard power access point needs to locate itself and then transmit its coordinates through the available spectrum inquiry request to the AFC server. And the AFC server queries its internal database to retrieve the nearby incumbent devices and calculate a suitable power and frequency level for the AP. That data is transmitted back to the AP by the available spectrum inquiry response message. So compared to the previous spectrum sharing system, the CBRS, Citizens Broadband Radio Service, AFC is much simpler. The AFC system does not require a professional installer and does not require a physical spectrum sensing device and also does not require any coordinations between the operators. That makes the AFC a low-cost solution suitable for commercial and home Wi-Fi systems. From the specifications, we identified 3 general security requirements of AFC system. First, the communication between the AP and the AFC server needs to be mutually authenticated, encrypted, and integrity protected. Second, the integrity of the internal AFC databases should be ensured. No unauthorized access or modification to these databases. Then we have the AFC server must provide accurate interference protection. That means the AFC server needs to calculate the estimated interference correctly and assign the correct power level to the standard power access point. With these requirements in mind, we ask the following question. Are these requirements enough to keep the AFC system function as intended? That means the AFC system should provide correct frequency and power to the standard power access point without interfering with the incumbents. Here comes our threat model. In our case, we assume that the AP is operating unaltered and the communication between the AP and AFC server is secure. Also, the AFC server is operating normally. With that assumption, can an attacker still attack the system controlling allocated frequency and power to potentially over or under allocate even without physical access to the AP? To answer this question, we look deeper to the possible attack surfaces. So first we have our AFC operation at the bottom, it is usually protected by TLS in the implementations we studied. However, before the AFC operation, we have several prerequisites. For example, we need the DNS query to find the IP address of AFC server, and to make the AFC work, the AP need to obtain a correct time from the network. So we have NTP here. Also, we have GPS and Wi-Fi for the AP to locate itself. So the first part is that from the DNS and NTP protocol, and network attacker is able to interrupt with the AFC operation. Here we know the DNS and NTP protocol are often used in plain text without any authentication or encryption. In that case, a network attacker is able to inject plain text packets to the AP to interrupt with the network protocols. And also, the GPS and Wi-Fi signals are attackable from a wireless attacker. The attacker can generate fake GPS or Wi-Fi beacon frames to the AP to mess up its location. Here I want to discuss about location spoofing attacks against AFC systems. First, we have a fixed link transmitter and receiver pair, and then we have a standard power access point located nearby. In its normal operation, the AFC system should assign correct power level to the AP, so the AP will not interfere with the existing transmissions. However, when a location spoofer comes into place, it can spoof the AP into sync itself at a different location. For example, some area without any incumbent transmitters. In that case, the spoof location will be transmitted to the AFC server, and the AFC server can provide a much higher power level for this AP. That causes interference. We have two main types of localization techniques implemented on the AP. The first one is GPS. So to spoof the GPS, to calculate its location, the GPS receiver needs to receive its wireless signal from multiple satellites. Let's say in our figure, we have satellite A and satellite B. And when an attacker comes into place, the attacker can transmit the signal as satellite A and satellite B to the victim receiver. So when the victim receiver receives the spoof signal, it will sync itself as the original GPS receiver's place instead of its true location. Similarly, Wi-Fi position spoofing can also be achieved by sending wireless signals. So in our case, let's say our AP is located at State College, and it scans multiple Wi-Fi networks nearby, and it will send the network information into a location server, and the location server will return back its coordinates to the AP. When an attacker is present, the attacker can spoof multiple APs in a different area, for example, New York City, to the target AP. And in that case, when the AP is scanning the nearby network environment, it will send a mix of the true Wi-Fi networks and fake Wi-Fi networks to the location server. And the location server will be fooled to provide a coordinate as in New York City to the AP. In summary, we find 6 attacks on the AP side and 1 attack on AFC server side in this work. We have tested our attacks on 4 different devices from different vendors, and 2 of them are using GPS to locate itself, and the other 2 are using Wi-Fi-based positioning mechanism. We also find that all of the tested APs are using plain text DNS, and only 1 of them, the routers, are using a secured version of NTP protocol. Our experiment, we conduct our experiment using a software-defined radio, USRP B210, cost only $2,000. And we modify open source softwares, GPS SDR-SIM and GR80111 to generate the spoofing signals. Here we have a demo on Wi-Fi location spoofing on one of our APs. So first, as you can see, on the left side is the shell from our AP, and on the right side is the shell from our spoofer. First, we run Wi-Fi positioning without any spoofing, and the AP is communicating with the server and send its and send the nearby network information to the server. After that, the location server returns a coordinate to the AP, which will be used in the following AFC request. However, in the next time we start our spoofing shell, we retrieve like 5 different APs from New York City and send its information to the AP. And then we run the Wi-Fi positioning again. In this case, the AP sends a different set of Wi-Fi networks nearby to the server, and the server returns the coordinate from New York City. With that spoofing attack, we can successfully launch our interference attack. We can spoof the AP into a rural area where no fixed link devices are nearby, and then the AFC server is able to provide the maximum power and all frequencies to the AP. So here the maximum transmission power is 36 dBm as defined in the standard power AP spec. And we are able to launch different kind of denial of service attacks where no channel is available for the AP, so the AP cannot transmit any signal on the 6 GHz. We can do it by spoofing the AP to an invalid location. For example, we spoof it to Japan where the standard power 6 GHz is not available, or we can send the GPS signal using an invalid time step. And we can do NTP and DNS spoofing to interrupt the AFC operation. Our previous attacks only works once in 24 hours because the AFC request only send once in 24 hours. However, in our last attack, we call it forced location update attack. We use a known vulnerability on the AP side to force the AP send the AFC request immediately. So it is a vulnerability related to NTP protocol that allows an attacker to inject a time to the vulnerable AP. We do it first by inject a future time, let's say 24 hours in the future, and we expire the previous channel allocation. So the AP will need a new AFC request. Then we set the current time back in the AP again, so the AP can successfully complete the following AFC operation. After that, we use our spoofing technique to inject a fake location to the AP. So the AP will send a new AFC request with the spoof location. In that case, we can launch the previous attacks A1 to A5 at any time. Other than the findings on the AP side, we also find potential resource exhaustion on AFC servers. So in our experiment, we find that the AFC server's API response time is correlated with the number of incumbent devices nearby. That means if the attacker can spoof the AP into a more dense area, the AFC server will process longer. And if the attacker can do it in a larger scale, it can cause severe resource exhaustion on AFC servers, which can cause the denial of service of all connected APs. So how can we defend against this kind of attacks? The most cost-effective way is geofencing. We think that the AP is usually operated in a fixed location. In that case, geofencing can be very effective. The AP only needs to register once when it is set up. And then if the AP moves outside of the desired location, we can the AFC server can just shut down its transmission. And this method is also recommended by HPE Aruba, as like in our discussion. We also have some other defense mechanisms listed in the paper. So please feel free if you want to check that. In conclusion, we see that the security of the AFC system is critically dependent on the integrity of its inputs, especially its geographic location. Also, this trust is misplaced, as demonstrated by practical low-cost spoofing attacks that can cause interference or denial of service on the 6 GHz AP. In addition, we think that defense against location spoofing should be considered to mitigate these attacks. Thank you, and I'm happy to answer any questions.